Hello everyone. This is the 12th week of this discrete mathematics course. So today I will talk about the assignment problems of week 11 and week 12, both of these weeks. Okay. So let's start with the problem 1 of week 12. Oh, sorry, this is from week 11. So the question was that considering the following statement. So consider the following statement and choose the right option. So there are 4 statements and we have to choose the only the correct option. The first statement is that the set of all non-zero integers from a group under the multiplication operation. So what is the set of all non-zero integers? So it is the set of all natural numbers that consist of the numbers 1, 2, 3 up to infinity. So all these natural numbers. So these are the set of all positive integers. So now we have to verify whether this forms with the addition operation, it forms a group or not. So for group, there are 3 properties. The first property was the closure property. So what does the closure property states? It states that if there are 2 elements A and B in G, then their composition, A composition B, also must belong to G. Now over here, for the set of natural integers, so if we consider A and B will in the set of all natural numbers n, then A plus B, the addition of these 2 integers, that is again a positive integer, and therefore we can say that that also belongs to A. So definitely the closure property is satisfied. The second property was associative. Now associative property is very easy to verify because for this case, for associativity, this must be true for all A, B, C in N. Now definitely this is true because as we know that if we add to integer, it doesn't matter whether you are adding it from the right hand side or the left hand side. So this always is true. So associative property is also true. The third one was identity. So what was this identity property? That means that there must exist some element. So this is under multiplication operation. Sorry. So basically, the things are almost the same because if we multiply two positive integers, then again that will be a positive integer, and therefore we can say that this multiplication is closed under this multiplication. Multiplication is closed under sorry, this set of natural number is closed under this multiplication operation. Similarly, the multiplication operation is associative because the multiplication from the left hand side or the right hand side is basically the same. And The third operation was the third property was the identity property. That means that there must exist some element E such that A composition E should be equals to E composition A, and that should equal to A for all A. There exists E such that this is true for all A in G. Now the question is, does there exist any element in N? So definitely there exists an element, because we know that 1 is a positive integer, and therefore 1 multiplied with any integer any integer A, that gives us A for all A in the natural set of all natural numbers. So therefore the identity property is also satisfied. But the problem is the final property, which is the inverse. That is, it states that for all G in G, there exists an element G inverse. So G inverse is basically a notation in G such that G compose G inverse should be equals to G inverse compose G should be equals to the identity element. So over here there must be some element. So for all A in the natural number set N, there exists some B such that the multiplication of AB should be equals to BA should be equals to 1. But that is not possible, because if A is an integer, in fact if A is a positive integer, then B does not belong to N, because you know that for a positive integer N, this B is nothing but 1 over N, but this 1 over N is not an integer. So therefore this inverse property is not satisfied, and the first one is not a group. That is, the set of all non-zero integer under multiplication operation is not a group. The second statement was that the set of all rational numbers forms an abelian group. Okay, so the set of all rational numbers. So what is the set of all rational numbers? The set of all rational number is basically of this form, P over Q, such that P, Q are integers and the GCD of P and Q is 1. So this is the set of all rational numbers. Now we have to see whether this set of all rational number is a group under addition or not. Now, so the closure property was that if we consider two elements like this, A, B, and C over D, both are in Q. Okay. So if we consider two elements and we add those two elements, then we will basically be getting this. Now we can find the GCD of these two integers. So this is an integer and this is also an integer, because this A, B, C, D are all integers. So therefore we can say that this is a ratio of two integers. Now we can find the GCD. Let us consider that GCD is D. Then, oh sorry, not D. So let us consider that GCD is basically G. Then we can consider P1 as AD plus BC over G1. Over G, and P2 as BD over G. And then this P1 and GCD of this P1 and P2 would actually be 1. You can verify that, okay, because we are just dividing the GCD from both, these two terms. So therefore P1 and P2 should have the GCD 1, and this P1 over P2, that should be exactly equal to this AD plus BC over BD. So we can get two co-prime integers such that the addition of these two integers is exactly equal to this the ratio of these co-prime integers. So therefore we can say that this P1, P2 do belong to Q. So this was the closure property. Now similarly, if the closure property is satisfied, then the associative and the associative property is very easy to verify. The associative property basically states that if we have sorry if we have A, B, C in Q, then the addition of two rational numbers and then we add C, this should be exactly equal to, and this is the property of the addition operation over over the all real numbers, not only the rational numbers but all real numbers. So this property is true. The associative property is also true. So closure property is true, associative property is true. What about identity? Now for identity property, we know that uh, 0 2 belongs to this set of all rational numbers, and if we consider any rational number A and we do this, then we will find back A, and this is the property of 0. So there is nothing new about it. So 0 is our identity element over here. And finally, we have the inverse property. So for inverse, we need to find inverse of an element. So if we consider P over Q in the set of all rational numbers, such that the GCT of P and Q is 1, then the inverse of this element, so inverse is basically inverse with respect to this addition operation. So that should be minus P over Q. Now, this minus P over Q is nothing but the ratio between minus P and Q. So now the question is, what is the GCT of minus P over Q? If the GCT of PQ is given as 1, then can we say that GCT of minus P over Q is also 1? So since GCT of P and Q is 1, so if we do show that, then we can say that this also belongs to Q, and then we can say that the inverse of each of the elements do exist in Q. Okay, so then Q would be a group. So we need to only prove this one. GCT of this is actually equal to 1. So if GCT of P and Q is 1, then from Bezier inequality we can say that there exist x and y integers such that Px plus Qy is equals to 1. Okay, since 1 is the GCT. Now again, we can write it like this, is equal to 1. That is, for minus P and Q, for these integers, we also have two integers minus x and y, such that this is actually equal to 1. And this is only we are only rewriting this equation over here. Okay. So definitely the GCT of minus P and Q, this is also equal to 1. So this is true. And from there we can say that this is the identity. So these do belong to Q, and therefore this Q is definitely a abelian group under the addition operation. And what about the abelian property? The abelian means that, so when we are saying abelian, so it means that for all A and B in G, we must have B composition B is equals to B composition A. And in rational numbers, so if we consider two rational numbers A and B in Q, then it doesn't matter whether we are adding it from the right hand side or the left hand side, and therefore we can say that this is true. I mean, there is nothing new about this. This is the addition property. So this is an abelian group. The third is the set of all real numbers from a group under the multiplication operation. Now, if we consider a group, if we consider the set of all real numbers, under the multiplication operation. Okay. So does this form a group or not? Now, to form a group, we need the closure property. The closure property is satisfied because if we consider any two elements in R, then definitely the multiplication of that is also in R. The associative property is also very easy to verify because if we, it doesn't matter whether we are first multiplying A with B and then we are multiplying C, or we are multiplying first A, B, and C, and then we are multiplying it with A. So these are basically same for all ABC in R. So these two are true. Third one is the identity property. So basically for all, so the identity elements, the property identity says that there must exist an E such that for all A, this is true, and definitely there exists an element, and that element is nothing but 1. So if you consider any element in R, then A, this is actually true. And finally, the inverse property. The inverse property says that for all element, there must exist some element B such that AB is equals to BA is equals to 1. Now, this is where this property does not hold, because if we consider the element A to be 0, then for 0, there does not exist any element B such that we multiply B with 0 and that gives us 1. So this is not possible in R, and therefore this 0 is the only element that does not have a inverse, and therefore this is not a group. And finally, the set of all odd integers under the addition is a subgroup of set of integers under addition. So set of integers under addition is definitely a group. Now in order to the set of all, so let us consider this O with a set of all odd integers. Now if this has to be a subgroup of Z, then all the property of group should satisfy in O. Now if we consider any two elements A and B in O, so that means that both A and B are odd integers. Now if we add these two integers, now addition of two integers, this is even integer. So definitely A plus B does not belong to O. So O is not closed, and therefore this is not a group. So only 2 is correct. The second problem, this was given as this, that in a group G, we are given that the computation, the Diffie-Hellman problem is hard. That is, if we are given only G to the N and G to the B, then we have to find G to the AB. So this problem is hard. Now we have to verify whether all these F1, F2, F3, and F4, if these are hard or not. That is given G to the A and G to the B, we can compute this value that is given over here or not. So now, if we are given a problem and we are said that this problem is hard, and we have to verify whether this P2 problem is hard or not. So how can we do that? So if we can show that if solving P2 gives us a solution for P1, okay, so then, and since we have already assumed that P1 is hard, then P2 should also be hard. So basically we will assume that P2 is we can have a solution for P2, and then from there we will derive a solution for P1. That's what we are trying to do here. Okay. So the first function is given as G to the A, G to the B is equals to A, B plus 1. Now we are already given G to the A, G to the B. And from there, suppose that we don't know whether it is hard or not. So basically we are given there g to the a, g to the b, and from there we have to find g to the ab, and this is considered to be a hard problem. So these are the hard problem. Now what can we derive? So basically from f1 function, so suppose that we don't know whether this f1 function does belongs to this hard part or this easy part or not. Okay, so let us consider this f1 function is over here, and this f1 function, it gives us this value g to the ab plus 1. Okay, so now what is this value? This value is nothing but g to the ab multiplied by g to the a. Now we do know g to the a, and we also know the extended Euclidean algorithm, and using that extended Euclidean algorithm we can find the g to the a inverse, the inverse of this g to the a. Now after we find this g to the a inverse, we can, so let us consider this as x, then we can just derive g to the ab as, and if we consider this as y, then we can consider g to the ab as y x inverse, and we can very easily compute that. So that means that if this is easy to compute, then we can very easily compute g to the ab. So definitely g to the a b plus 1 must be hard to compute. Otherwise, if this was easy, then definitely computing g to the ab would have been easier. Would have been easy problem to solve. And since the assumption is that this is hard to solve, then we can say that this is also hard to solve. Okay, so this was the f1 function, and similarly, now we have f2 function. So the f2 function says that, okay, so this was f1 function. Now the f2 function says that given these two values, we can get y is a plus b. Now first, let us consider this. If we have g to the ab, then we can just multiply those two together, and we can get this, let's say z is equals to g to the a plus b. So computing this g to the a plus b is very easy, and then we just have to do a square, and the z square would be our g to the 2a plus b. So computing g to the a plus b and g to the 2a plus b, these are both easy. So these are not a hard problem. So whether we can compute this or not, that doesn't give us any information about this g to the ab or g to the a plus b. Sorry, g to the a multiplied by b plus 1. So definitely solving this f2 and f3, these are easy. And what about f4? So in f4, the function, this computes g to the twice ab, and from there we have to find g to the ab. Now consider this. We know that in a group, so if we consider a group, so if the group is G, then the order of the G, let us consider that to be n. Okay, now G to the twice ab, that is given to us, and we know that G to the n is actually equals to 1 for all G in G. Okay? And G is given as the generator, so anyway, so G to the n is 1. Now what we will do is that we will find uh, 2 inverse mod n. That is, we will find the 2 inverse. So let us consider B to be the 2 inverse mod n. Okay, so that means that 2 multiplied by B, that should be congruent to 1 mod n. Okay, so in modulus n, we will find this inverse of 2. Now that is only possible when the GCD of 2 and n is 1, that is n is odd. So So basically, in any setting, so in cryptographic settings, so the order of this group is usually taken as prime, or rather, the order of this group is taken as odd prime. So therefore, we can assume that this n is odd that is given to us. Okay. And okay, so anyway, so if we consider this, then we will have this, and from there we can say that this 2b is nothing but nk plus 1. Okay, so now we are okay, not b. So let us consider this as some other integer, let's say p. Okay, so this t is nothing but the inverse of p, and this k is another integer. So t and k are some integers. Now we are given this g to the 2ab. So if g to the 2ab is given, twice ab is given, so what we will do is that we will just take the power to t. So basically we will be computing this g to the 2ab to the power t, and that will give us g to the twice of t multiplied by ab. Now twice of t is basically this nk plus 1, so that should be nk plus 1 multiplied by ab. And if we compute this further, then we will see that this is nothing but g to the 8. So if g to the twice ab is given and n is odd, the order of the cyclic group is odd, then we can definitely compute this very easily. So this is also a hard problem. Okay. So a and b, computing a and d, these two functions are hard. Now we have to compute the Euler-Torsion function. Now, so there are two things that we have to understand over here. Is that first one is that the Euler-Torsion function is basically a multiplicative function. That is, we can write this where GCD of Mn is 1. If m and n are co-prime integers, then we can write that phi of Mn is nothing but the multiplication of phi m and phi m. So how do we prove this? So this proof is comes from Chinese remainder theorem. So suppose that we are given this group, that is all those elements that are co-prime to Mn. Okay? And over here we have an element. Sorry, we have this group over here. Not this. So this is the set of all integers that are co-prime to Mn, and this is basically the pair of all integers, such that the first one is co-prime to M and the second one is co-prime to M. Okay. Now, if we consider any element C over here, we can map it to this Mn in this way. That C should be, so this should be AB, such that A is congruent to sorry, C is congruent to A mod N, and C is congruent to B in mod M. So under modulus M, this C gives us A, and under modulus N, this gives us modulus B. Okay? So this is how we are mapping this. And Chinese remainder theorem says that if we have A and B and M and N are co-prime, then we can definitely go back to C. Unique. I mean, we will find a unique C such that this satisfies this linear equation. So this so now we have to prove that this mapping is a bijective mapping, and if this is a bijective mapping, then the size of this set would be phi m cross sorry, multiplied by phi n, and the size of this set is nothing but phi m. And if we can prove that this map that we have defined right over here is a bijective map, then we can definitely say that this is true. So how do we prove this? So first of all, we will assume an element over here, that is C in ZMN star. That is, GCD of C and Mn is 1. And now we have found A and B, this pair AB, such that C is congruent to A mod n and C is congruent to B mod n. Now we have to prove that since the GCD of this is our assumption, the GCD of C and Mn is 1, then we have to prove that the GCD of A and N, sorry, over here this should be M and this should be N. So A and M and B and N, both of these should be 1. So we will prove this by contradiction. So assume that D is the GCD of, so first we will consider this GCD of A and M is D. Now these can be written as C is equals to some mk plus A, right, where k is some integer. So this so anyway we can write it like this. Now GCD of A and M is D, so that means that D divides A and D divides M, because this is the common divisor of this A and M. This is the greatest common divisor, but first of all this is a common divisor, so both A and B are divisible by T. And since both A and M are divisible by T, so then this equation, this term over here, this is also divisible by D. So that means this implies that D is divisible by C. Now D divides M, so this implies that D divides Mn, this term over here. So D is a common divisor of both C and Mn. But we have assumed that the greatest common divisor of C and Mn is 1. So therefore, D must be 1. So the greatest common divisor of A and M, this is 1. And similarly, if we consider the greatest common divisor of B and N to be some D value over here, then also in the similar method, we can prove that D has to be 1. So both of their GCD, that is GCD of A and, so A must belong to Zm star and B must belong to Zn star. So that is our conclusion. So if we have a C, then this A and B must belong to Zm star and Zn star. Now conversely, we have to prove that if we consider these two elements, Zm star and B belongs to Zn star, then we know that using Chinese remainder theorem, we can have a C such that C is congruent to A mod n and C is congruent to B mod, M, and this is congruent to B mod n. Then our, okay, and C belongs to Zm. C belongs to Zm. Our claim is that this GCD of C and Mn, these also must be 1. Okay. So if not, let us consider that the GCD of C and Mn is basically D. So that means that D divides C and D divides Mn. Now C, so first of all, let us consider that so if these are true, then we can write that this can be written as A plus some mk and B plus some in k dash. Now M and N are co-prime, so that means that D divides Mn this can imply either D divides M or D divides M, not both of this. Okay, so let us consider without loss of generality that this D divides M. So if D divides M and D divides C, so that will imply that from this equation we can say that we can rewrite A as this C minus MK, and since both C and M are divisible by D, then we can say that D divides A. Now D divides A and D divides M. These imply that the GCD of A and M is equal to D. Oh, sorry, not GCD of A and M is equal to D, but GCD of A and N has to be greater than D. But that is a contradiction, since we have assumed that this GCD of A and M is actually 1. So D must be 1. And similarly, if we consider D divides M, then from this equation and the fact that GCD of B and N is 1, we can conclude that that the GCD of C and M, this must be 1. So therefore, we basically have a bijection over here, and that proves this statement over here. That is, if M n are coprime, then phi of M, phi of Mn has to be phi m times phi n. So this is proven. Now the second one is that, so any integer n, this can be written as p1 times alpha 1, so p1 to the power alpha 1, p2 to the power alpha 2, up to pk to the power alpha k, where this all p1, p2, pk are all prime integers. And since they are prime, so we can write this p1 to the power alpha 1, p2 to the power alpha 2, these are all co-primes. So phi of n, this can be written as phi of p1 to the alpha 1, phi of p2 to the alpha 2, and so on. Now, what is the value of this phi of p1 to the alpha 1? So you can look it up. This is very easy to see. I mean, the counting the number of co-prime integers that are less than p1 to the power alpha 1, and that is coprime to p1 to the power alpha 1. So if n is equals to of this form, p1 to the alpha, then phi of n is actually of this form, p1 to the power alpha 1 multiplied by p minus 1. Okay, so you can look it up yourself. This is very easy to see, and so therefore this phi of n should be computed as this, or we can write it also in this way. We can write it as p1 to the power alpha multiplied by 1 minus 1 over p. We can also write it like this. So this should be actually p1 to the power alpha 1, p2 to the power alpha 2, up to pk to the alpha k multiplied by 1 minus 1 over p1, 1 over p2, up to 1 over pk. So this is n multiplied by 1 minus 1 over p1, 1 minus 1 over p2, 1 minus 1 over pk. So this is how we compute the phi of n. Now, the number that is given in the question is 2 to 1. So if you consider phi of 2 to 1, so that is nothing but 13 multiplied by 17. Now, if we use the formula that we have, so if we use this formula over here, then that will actually give us 13 minus 1, 17 minus 1, and that is 192. So this is our answer. Okay, so now let's get to the problem 4. So in this problem, we are given uh, 4 statements and we have to choose the correct option only. So the first statement is the sender and receiver need to exchange their respective secret values to communicate over the public channel using the in-kernel encryption. So let's look at the in-kernel encryption scheme again. So in the in-kernel encryption scheme, we have Alice and Bob, these two parties. So Alice has a message and Bob want to receive that message. So what do? So basically Alice, sorry, first Bob chooses some A and computes G to the A. This G is basically public. So G is basically a generator of some group G. Okay. So this G is public. G and this group G, these are all public. So Bob first computes this G to the A and sends it to Alice. Now what Alice does is that Alice have a B, generates a B, randomly samples a B and then computes G to the B. And also it computes G to the A. So whatever the G to the A is, or that is given as Y, let's say. So it computes Y to the B and then multiplies the message on with it. Now let's compute it as X. So Alice now sends this X, G to the B, X and G to the B. Only these two values are sent to Bob. Now what Bob does is that Bob would now compute, and let's consider this G to the B as let's say R. So Bob computes R to the A and then it inverts with X, and that gives us the message here. So this was the L-Gamal encryption scheme. Now in this whole process, the secret was basically this A over here that Bob generated. So this was the secret, and this was never shared. In fact, Bob only shared this G to the A, and from the hardness assumption, we know that from the given G to the A, the computing A, this is the discrete log problem, and this is very hard. There is no efficient solution in classical computers to compute this from given this G to the A to compute this A. There is still no known efficient algorithm. Okay. So Bob can. So basically, Bob doesn't share the secret value with Alice. So this is not true. In the public key channel, L-governed encryption scheme does not. So sender and receiver does not have to exchange their respective secret values. So this is not true. Now the second question says, the second statement says that in a secure crypto system, the encryption and the decryption algorithm are publicly available. So this is true. In fact, this is there is a rules called Karshav's principle. It says that uh, only the secret value should not be known. So if we are using some encryption method and some decryption method, the design of that encryption, I mean, that means how. So if we give a key over here and there is some message over here, and after the key is given to this encryption method, then it gives us ciphertext. And at the decryption protocol, we input a ciphertext, it outputs the message, and the same key or maybe some other key, depending on whether the scheme is a symmetric crypto system or a public crypto system. So it might be PK and SK. For a symmetric crypto system, these both PK and SK are same. So anyway, so these are basically some design, and these design are publicly known. Okay? So these designs are publicly known. The only unknown part is this secret key. And according to the Karsos principle, a design is a cryptographic protocol is considered secure if their design is publicly known, but only the secret value is private, and yet we cannot get any information about the message or the secret value. Then we can consider this uh, system, this crypto system, to be a secure crypto system. So anyway, so basically this is true. This statement is true. That is, in a secure crypto system, the encryption and decryption algorithm both are publicly known. The algorithms are only known, okay, not the secret key. Secret key is not part of the algorithm. So anyway, the third statement is that when the data is encrypted using cryptographically secure algorithm and sent through the internet, it is guaranteed that it is always received correctly at the other end. So this is also not true. Why? Because we have Alice and Bob. Now Alice is trying to encrypt some message, maybe with some key, and it gets the ciphertext. Now this ciphertext is actually sent to Bob through some public channel. Now in this public channel, there is some other adversary, let's say Eve, is always there and sniffing on the network. So what Eve can do, Eve can play as a middleman. So Eve can just disrupt the whole communication between Alice and Bob, and it can so it is possible that all the communication is first coming to Eve, and then Eve is channeling that communication back to Bob. So this Eve can be some internet service provider or anyone. Okay, so this ciphertext is first sent to Eve. Now Eve can, Eve can in change the ciphertext and compute some C dash, and this C dash is now sent to Bob. Now it might be possible that this C dash, after decrypting this C dash, Bob might not get any value at all, or any valid plain text at all. But the point is that if can change this ciphertext, so it is not always guaranteed that that it is always received correctly at the other end. So this is not a guarantee, because the public channel is there, and it is not a secure channel. But this kind of guarantee can be encountered if we use something else other than only cryptographic systems. So those have been discussed in some other courses. You can look that up. Okay, and the final thing is that the final statement is the RSA crypto system can be broken if the order of Z star is known. Okay, so let's look at the RSA crypto system first. So in the RSA crypto system, we had two prime numbers, P and Q, and then we had n as the product of two prime numbers, and then we had phi of n, and phi of n was computed as p minus 1 times q minus 1. So this is the order of Zn star. Now the question is, if we make this public, this phi of n public, is it possible that we can generate the secret value? So now the public key was basically, so what was the public key and what was the private key? The public key was basically this n and some e, where this e was some element from Zn star. That is GCD of oh sorry, not Zn star, but this should be Z phi of n. This is the order of Zn star. That is the GCD of E and phi of n. This has to be 1. And if this is 1, then using the using the extended Euclidean algorithm, we can compute this D, which is such that we can compute this D such that ED has to be concurrent to 1 mod phi of n. That is the multiplicative inverse of E. That is what we can compute using the extended Euclidean algorithm. So this N and E, this has to be public and this has to be private. Now, if somehow the attacker or anyone else other than the key generator, if someone gets hold of this phi of n, if it doesn't do know the phi of n, then what happens is that it can very easily, using this extended Euclidean algorithm, it can generate this D. So D would be known to the attacker, and therefore RSA crypto system can be broken if this order is known. So this is also true. Okay, so this should not be our answer. That is choose the correct options. Okay, so this is a correct option. Oh, sorry, this is our correct option. This is not. So 2 and 4 are the only correct options. Okay, so in problem 5, we are given this group, and this is a finite abelian group of order n, and the identity element EG, identity element is given as E of G, and we are given X as the composition of all the elements in G. So the G has order n, and all the elements A1, A2 up to An, these are all composed together, and we are given that element as X, where G is equals to, so basically it says that A1 to An are basically all the elements of G. So what is the value of X to the 2 to the 16? Now, from the inverse property of group, it says that for each element A, there exists an inverse B such that AB is equals to BA is equals to E of G. So this is true. Now, there can be two cases. Case one is that A and B are distinct. That is, the inverse given an element, the inverse element is basically some other element. So that is possible. And case two can be that A and B are equal. That is, element is an inverse of itself. So there can be these two cases. So now we are given this element A1 to 2 up to, sorry, this G is given as the set of all elements from A1 to up to An. So now we divide this set into two parts. The set of all elements that have order only 2, set of all elements that belongs to this case 1. So let us name it as G1 and G2. These are not subgroups. These are basically some sets that we are dividing into. Okay. So G1 basically contains all those elements that have their inverse. I mean, the inverse of those elements are completely different from that element itself. Okay. So in this case, A is not equals to A inverse. So G1 is basically all those elements, and G2 is the set of all those elements where A is equals to A inverse. Now, if we multiply all the elements in G1, okay, so A1, A2, so let's say A1 dash, A2 dash, up to let's say A T dash. If we multiply all the elements, so then each element would have their inverse element. So basically, if we consider this, that if A belongs to G1, then the claim is that A inverse also belongs to G1. Why? Because A is not equals to A inverse, and the inverse of A inverse is nothing but A, and therefore the inverse of A inverse itself is not equals to A inverse, and therefore A inverse also belongs to G1. So anyway, and therefore we can say that if we compose all the elements in G1, then that will give us the identity element E of G. Now what about G2? And since all the elements are commutative, then therefore this is also true. Okay, so let us consider. So since this is commutative, then we can say that this is this can be written as like this: A inverse inverse, A2 dash compose A2 dash inverse, and so on. we can write this term like this. Okay. Now in G2, the thing is that all the elements are basically like this, that is A is equals to A inverse. So if we square those elements, that will give us E of G. Okay. So this X, which is basically written as like this, suppose AN, we can now write it as this, A1 dash compose A2 dash compose AT dash, that composed with let's say some B1 dash, sorry, not dash, so some B1 compose B2 compose to Bn minus T, where this G2 is the set of all this B1 B2 up to Bn minus T. Now we have already established that this has to be one. Sorry, this is the identity element, and if we compose anything with the identity element, that gives us this element itself. So this will be Bn minus T. Now if we do an x square, so if we square this element, so since this is a commutative group, then we can write it like this: B1 square, B2 square, compose Bn minus T square. And we can, if x is equals to this, and x square can be written only because of the commutative property. If the group was not commutative, then we couldn't write this. Okay. So after we, now we know that each of this B1, B2, B3, these are in G2, and the property of G2 is that each of the element, if we square those elements, then that will give us the identity element. So these are basically the composition of all the identity elements. Not all the identity elements, but basically identity elements only. Okay. So that will finally give us the identity element. So from here, we have established that x square is identity. So if we take any even power, even 2016, so this is an even power of, let's say, 1008, I think. Okay. So this is nothing but the identity power, some power over there. So any even power should be identity. Any even power of x should actually be the identity element. So x to the 2016 is identity. Okay. Now we will look into the problems of week 12. So in week 12, where we have been introduced to fields and rings. So over here we need an example of division ring. So what is a division ring? So division ring is basically have all the properties of a ring, that is, sorry. So let us consider this R plus dot. Okay. So this is a ring. Now this ring is called a division ring when this R plus is a group, R dot is a non-commutative group. Non-commutative is not necessary. This is also a group. Now remember the property of a field. So what was a field? So field says that R plus should be, okay, so this is an abelian group. The R plus is an abelian group, and R dot is also a abelian group. So with respect to addition and multiplication, both has to be an abelian group. But over here, only the R plus has to be an abelian group, but R naught may not be an abelian group. So those kind of rings are called a division ring. So that means that with respect to dot, each of the elements should have a multiplicative inverse, but the elements may not commute with respect to this dot operation. So what is an example of such a ring? So one example is GL2R. So what is this? So this is basically the set of all 2 by 2 matrices such that the determinant, okay, such that the determinant of this matrix, so let us consider this matrix to be M. So determinant of this matrix is 1. Not okay, so non-zero basically. Determinant is non-zero. And all these A, B, C, D belongs to R. That is all the 2 by 2 singular matrices. So if you consider this, then this actually forms a division ring. Why? So first of all, if we consider, okay, sorry, this is not division ring. Because with respect to addition, this will not be a, so this is a ring, but not division ring. Okay, so there, so example of a division ring. So anyway, I think that, okay, so this matrix, so matrix is this basically forms a ring. So if we consider any GL in R, so this is basically some m by n matrix. So M is n cross n matrix such that the determinant of M is non-zero and M belongs to R n cross n. So R n cross n means that this is a matrix of where the each of the entries comes from R, the real numbers. Okay, so this is the set of all GNR. Now, as we can see, if we consider any, if we add any two integers. Okay, so yes. So this is a division. Sorry. Okay, so if we add any two matrices, M belongs to a matrix GLNR, and N is also a matrix GLNR. If we consider any two matrices, then if we add those two matrices, then definitely that will be again a matrix, and each of the entries are from the real number set. So that definitely belongs to GLNR. In fact, you can consider 0 to be all the entries, all the n cross n entries to be 0. So this is the identity element with respect to the addition operation. So if you consider m plus 0, that will give us m, and again 0 plus m, that is also give us m for all m. So addition, you can see that with respect to addition, this set is basically creates an abelian group because m plus n is n plus m. There is no problem with that. Okay. So this is true. So this is an abelian group. R plus is an abelian group with respect to, sorry, GLNR. This actually forms an abelian group with respect to the addition. Now, what about the multiplication? Now, with respect to multiplication, it also forms a group because if we consider the multiplication of two matrices, then what is the determinant of M and N? So we know that determinant of M and N is nothing but determinant of M multiplied by the determinant of N. Okay. And since both of these are non-zero integers, So we can say that determinant of Mn is also non-zero. So therefore, closure property is satisfied. Closure property is, so that is in R is closed under dot. Okay. So under the multiplication operation, this is closed. What about the associative? So associative property is also held, because if we consider this M in R, okay, that can give us M in where this M in R all belongs to this. So we can verify that for a matrix this is true, right? Now, the third property is the identity. Now, if we consider I of n, which is basically all the diagonal values are 1 and rest of the values are 0, the identity matrix basically. If we consider this matrix, then we can say that for any matrix M, this min is equals to INM is equals to M. So this is true. So this is our identity element, and also the determinant of In is equals to 1. So that implies that In do belongs to this set. Okay. And the next property is the inverse property. For the inverse property, we know that if given a matrix, if the determinant of the matrix is indeed non-zero, then that matrix is called a singular matrix. And given that matrix is called a non-singular matrix. And any non-singular matrix is invertible. That is, we can get an M inverse such that this M inverse belongs to GLNR. And the determinant of this M inverse is nothing but 1 over determinant of M. Okay. So this forms a group. I mean, this GLNR, this forms a group with respect to this dot operation. But what about the commutative property? So the commutative property, we know that Mn is not equals to Nm for all Mn. That is, we can give some example for which the multiplication of two matrices is not equals to the multiplication. I mean, multiplication of M and N is not equals to multiplication of N and M. Okay, so this is not true. That is, the commutative property is not there for this ring over here, and therefore such ring are called division rings. So the only difference between a division ring and a field is that this R dot in a field, this R dot is a abelian group. In a division ring, this R dot is not. It does not necessarily have to be a abelian group. Okay. So in problem 7, we need to find a. So we have to prove this statement. The statement is that the polynomial ring over integers modulo an irreducible polynomial is a field. So that is, we are given this. So this is our ring R. Okay, and we have to prove that if Fx is irreducible, so this implies that R is a field. So how do we prove that? So Fx is irreducible. Sorry. Okay, so let us consider this as phi of x. Okay, so phi of x is a polynomial. So if phi of x is irreducible, then we have to prove that this R, this ring R, is a field. Now, how do we prove that? Now consider a polynomial fx. Now, we know that if Zx is a polynomial ring, and in Zx a polynomial ring, the Bezout inequality and the Euclidean algorithm, all of them are satisfied. So we can write this, that fx can be written as some qx multiplied by this phi of x plus some rx. Any fx can be written as this, where this rx, sorry, the degree of rx is less than the degree of phi of x. Either the degree is 0, sorry, yes. So this is the condition. So for given any fx in zx, so fx is in zx, we can have this, and this rx polynomial is, so this rx polynomial, so after, since we can write fx in this form, then this rx polynomial is basically the element in this ring R. So rx is the polynomial in this ring R. So this is how the modulo ring is defined. This quotient ring is defined basically. Okay. Now, in order to prove that this is a field, this R is a field, we already know that this R plus is a abelian group, and R dot is a group. Sorry, that is what we have to prove, that R dot is a abelian group. Now, if we consider in Rx, this polynomial Rx, I mean, in this way, then the GCD of Rx and GCD of Rx and phi of x, this has to be 1. Why? Because if not, then we can say that GCD of Rx and phi x is equals to, okay, so basically GCD of Rx and phi x is equals to some, let's say Tx, such that degree of Tx is equals to 0. That is, Tx is basically a constant, some constant value. So if not, then we can assume that this degree of Tx is greater than 0. Okay? And then that will imply that Tx divides phi of x and Tx divides R of x. Right? But that is not possible because Tx is a non-constant polynomial that divides phi of x, but we have assumed that this phi of x is irreducible. And therefore, this Tx polynomial must Tx polynomial cannot be a polynomial with degree greater than 0. So this is not true. So this Tx is nothing but a constant polynomial. Sorry, yes. So Tx is nothing but a constant polynomial. That is, it is only some field element. Let's say T, and T belongs to the field F. Sorry, some Z. Okay, it actually has to be unity. So anyway, this is a constant polynomial. Okay. Now, what we can write is that this Rx multiplied by some polynomial, let's say Px plus okay, this actually has to be a unity, that is 1. Px has to be 1. GCD of Rx and phi x. Now, in Rx, Rx and Px. So Rx can be written as, so since the GCT of Rx and phi of x is 1, so then we can write that there exists some Px polynomial and Qx polynomial such that this is true, and this is from the Bayesian inequality. And using the Bayesian inequality, we can write this. So now, if we consider this value in mod phi x, so Rx Px plus 1 plus phi x Qx in mod phi of x, that actually would give us Rx Px mod phi x. So this is congruent to this. Now this was again 1, so therefore we can write that this Rx Px is nothing but congruent to 1 mod phi of x. That is, there exists some polynomial Px such that this polynomial multiplied with Rx gives us 1. And again, using the same method, if Px is some polynomial that has degree greater than phi of x, then we can write Px in this form, and then we will get some R dash of x, and that R dash of x, and we can then show that Rx and R dash of x, for that also, this is congruent to 1 mod phi of x. Okay. So basically so if we consider any Rx in this ring, if we consider any random Rx in this ring, then arbitrary Rx in this ring, then for that arbitrary element, we do have a element P of x such that the multiplication of Rx and Px is 1 in modulus phi x. So therefore, we can write that this is a field. We don't have to prove the other properties. That is that is the identity element 1 exists in this field. We know that 0 does belongs to this field. So R dot is a group. To prove this, we don't have to. We know that R dot is closed, associative. Also, the identity element exists. These properties are already known, and also the commutative property. That is it is an abelian group. That is also known to us, because if we multiply two polynomials, then multiplication of ax and bx is basically same as bx multiplication of bx and ax. So commutative property is also known. The only property was the inverse property that was missing, and we have proved that inverse also exists in this ring. So therefore, we can say that this is a field. Okay. So now, from problem 8, we will be solving the problems that was given in the week 12 assignments. So the first option, so the first question was that we have to choose the correct options. So the first is that there are no divisors of 0 in a field. Now what is divisors of 0? So divisor of 0 means that, so if we consider any x element in a R, then x is called divisor of 0. Sorry, not a divisor of 0, but rather x is called a left divisor. X is called a left divisor of 0 if x multiplied by so if there exists some y such that x y is equal to 0. That is, if we there exists some y such that if we multiply x from the left hand side with y, then this will give us 0. And similarly, it will be called the right divisor if there exists some y such that y x is equals to 0. That is, if we multiply x from the right hand side of y, then that will give us 0. Okay. Now, usually, if the ring R is commutative, then left divisor of y or right divisor is basically the same, because yx has to be is equals to xy. So in those cases, we call x to be a divisor of 0. If this is true, then we call x as only a divisor of 0, not a left divisor or right divisor, but rather divisor of 0. Okay. Now, the question was that in a field, so if let us consider that x is a divisor of 0. Oh, and also we have to understand that the divisor of 0 has to be a non-zero element. That is, x is called a divisor of 0, and one very important condition is that x has to be non-zero. X is not equals to the 0 element. Okay. Now, let's say that x is a divisor of 0 in field f. Okay. So now there exists some y such that we can write that xy is equals to 0. Now, since there exists a y such that this is 0, and y is also non-zero, y has to also be non-zero. Okay. So now, since x is non-zero element, then we can write that x inverse exists, and therefore we can write that x inverse multiplied by xy, this is equals to x inverse 0. Now x inverse is multiplied with x, that will give us y, and that is equals to 0. Now this is a contradiction, because we have assumed that there exists a non-zero y such that this is true, and that only gives us that y is 0. And we can assume that this x inverse exists because we are considering a field, and in a field every non-zero element has a multiplicative inverse, and therefore this gives us the conclusion that y is equals to 0, which is a contradiction. So therefore x cannot be a divisor of 0. So this is true. The second one is that every ring is a field, but a field is not a ring. So this is basically not true, because we have shown an example of division ring. Right. So division ring is a ring, but not a field. On the other hand, if we consider a field, then it essentially has to be a ring first, because a field satisfies all the properties of a ring. So in order to be a field, it has to be a ring first. So field implies ring, but not the other way around. So field implies ring, but not the other way around. Okay, so this is not true. Now, option C says that r minus 0 plus dot is an example of a field. Okay. Now, if you consider r minus 0, then r minus 0 plus is not a group. Why? Because we are completely deleting this, we are completely excluding this 0 element. So therefore, with respect to addition, there is no identity element in this set. So identity element does not exist in r minus 0 with respect to the addition, and therefore this is not a group, and hence we can say that this is not a field. Now option D says that an irreducible polynomial over a field cannot be factored as a product of two non-constant polynomials. So this is also true. So let us say that this is not true. So let's say the phi x is irreducible. The phi x is irreducible, and we can write this phi x as the product of fx and gx. Actually, there is nothing to prove. This is the definition of irreducible polynomial. The definition says that an irreducible polynomial that cannot be factored into product of two non-constant polynomials. So if fx can be written as gx and fx, sorry, phi x can be written as gx and fx, then either the degree of gx is 0 or the degree of phi x is degree of fx is 0. That is, either one of them has to be a constant polynomial. Now, in problem 9, we have to find the greatest common divisor of the polynomials over a field. Now, there are two polynomials that are given. First one is ax plus a cube plus a plus 1, and the second one is a square plus 1. Now, if we are given two polynomials fx and gx, and we have to find the GCD of them, then we know that GCD of fx gx, so this was from the Euclidean algorithm, we can write fx in this form: qx gx plus some rx, where this degree of rx is greater or equals to 0 and strictly less than degree of gx. So we know this. Now, from Euclidean algorithm, we have seen that the GCD of fx, and if fx can be written as this, then the degree of GCD of fx gx is actually equal to the GCD of gx rx. And once we, so then again, we find the GCD, we can write gx in this form: qx multiplied by rx plus some r dash of x, and unless and until we get this rx to be 0, and once we get this rx to be 0, we can say that this gx is our greatest common divisor. Okay. So that exact algorithm we are going to use. So first of all, what we do is that we want to we consider this as fx and this as our gx, and we will find this. So this is our g of x, and this is rx, sorry, the fx is plus a plus 1. So we will divide these two polynomials. So this should gives us a cube plus a plus 1, a4 minus a square, a cube minus a square plus a plus 1. So this should be plus a cube plus a square plus 1, and finally we will have this. So if we divide, then we can say that this a6 plus a cube plus a plus 1, this can be written as the multiplication of a square plus 1 and a4 minus a square plus a plus 1. And therefore, the Rx is nothing but the 0. The Rx is 0 over here. So we can write that this GCD of a square plus 1 and a cube, sorry, a6 a cube plus a plus 1, this is nothing but a square plus 1. Okay, so we have found the GCD of these two polynomials. Now in problem 10, we have to find the false statement among these four statements. So the first statement is given as the degree d polynomial over fields will always have d many roots. So consider this polynomial x square plus 1 in R. Sorry, R of x. So basically all the coefficients are from R. So how many roots does this have in R? So the roots of this polynomial, as we know, are the plus I and minus I. But so these are complex numbers. So this does not belong to R, but rather this belongs to C, the complex numbers, the complex field. So basically, when we are actually stating the statement that the degree D polynomial over fields will always have D roots, so what it tries to say is that that it may not be that the roots are inside the field itself, but it may be some other field. So this field is called the extension field. Okay. So anyway, so this is the extension of a field is out of the scope of the syllabus. But anyway, the fact is that even though that this polynomial is irreducible in R, the roots of this polynomial do exist. The roots does not belong to the field itself, but it may belong to some other field. Okay. So whenever we are talking about a D degree polynomial, so we always have to remember that this D degree polynomial have D many roots. Okay. The second statement is that a monic polynomial of degree D is a polynomial in X. Polynomial in X is one in which the coefficients of the highest power of X equal to the unity. So this is the definition of a monic irreducible polynomial. Sorry, monic polynomials. So monic polynomials is that a polynomial can be written as this: a0. Sorry, any polynomial can be written as this: an(x) plus an minus 1 x to the n minus 1, so on up to a1x plus a0. So this is a polynomial. The monic polynomial, the definition of monic polynomials is that the highest power, this an, this has to be exactly equal to 1. It doesn't matter what are the coefficients of the rest of the powers of x, but the highest power always must have the coefficient 1. So this is the definition of monic polynomial. So this is just definition. So this is also true. The third statement is that the multiplicative group ZP, the multiplicative group ZP star, where P is prime, has P generators. Now this is not true. Why? Because ZP star only have P minus 1 many elements. Because ZP star is basically the set of all integers that are less than n and non-zero. Okay, so 1, 2 up to P minus 1. These are the elements that are in ZP star. So it has only P minus 1 many elements. So how can it have P many generators? Right. So anyway, what if the statement has have said that it has P minus 1 many generators? Is it true then? So that is also not true, because if we consider Z5, so Z5 has all the elements like this: 1, 2, 3, 4. So what is 1 square? The order of the group is 4. This is the order of the group. Now, in order to be a generator, 2 to the 4, sorry, in order to be a generator, g to the 4 has to be 1. And this is the lowest power such that this g to the 4 is equals to 1. Now, is it true for 1? So 1 definitely not true, because 1 itself is the identity element. So how can you just expect that 4 is the lowest power such that 1 to the 4 is 1? Okay, so this is not true for 1. What about 2? So 2 square, as we know, is 4, and then if we square that again, so 4 square, that will give us 16. So 2 square is 4, and then 2 cube, that is 8, and in modulo 5 we can write it as 3, and then 2 to the 4, that is actually equal to 1, because that is 16, and in modulo 5 that will be 1. So 2 has the order 4, because 4 is the lowest power, such that 2 to the 4 is 1. Similarly, uh, okay, so 3 squared is basically 9, so in mod 4 that should be 4. 3 cube, that is equals to 27, and in mod 5 that is 2, and then 3 to the 4, that is actually equal to 1. Okay, so 3 is also a generator, but not 4. Why? Because if you consider 4 squared, that should be 16, and in mod 5 that is 1. So 1 and 4 are not generator, but 2, 3, they are the generators in Z5. So there are even though the order of this group is 4, there are only 2 generators. So this is also not true, that if ZP is the group that we're considering, sorry, ZP star is the group that we're considering, this is not true, that it has P minus 1 generators. Okay, so this is not a true statement. And the option D says that if a polynomial, if fx is a polynomial, and if f of 3 is equals to 0, then 3 is a root of fx. This is also very easy to because in the lectures we had seen the proof that if fx is a polynomial, with f of alpha is equal to 0, then we can write f of x as x minus alpha multiplied by some gx. Now, if fx can be written as this, then definitely alpha is a root of f of x, because x minus alpha is a factor of fx, and that means that alpha is a root. We have seen the proof in the lectures, so this is true. So the only false statement was the statement C. Okay. So in problem 11, we are given that Alice. Okay, so Alice and n minus 1 of our remaining friends have each nt summary secrets here, and Alice wishes to reconstruct the secret. And S many friends sends Alice the incorrect values. So which one of the following statements are true? Now, in summary secret sharing, what have we seen? That in summary secret sharing, first, whoever is the issuer, so he basically the dealer selects a random polynomial. Okay. So if there are n many parties, or rather, let's say that the size of the polynomial is, degree of the polynomial is t. Okay, a t degree polynomial is selected, and then for n many parties, there are already some alpha 1, alpha 2, alpha 3, alpha 4 to alpha n. So there are n many points at which this n many parties can generate their n many parties can evaluate this polynomial. Okay. So what the dealer does is that dealer evaluates this polynomial fx. This fx is a secret polynomial. Okay, so this is secret. This secret polynomial is evaluated on all of this alpha 1, alpha 2, alpha n, and these are publicly known. So after evaluating these points, it gets some value, f of alpha 1, f of alpha 2. So we can write it as S1, S2, S3, S4 up to Sn. So these are the shares that are shared among all the parties, n parties. And the secret is this point. That is evaluation of the polynomial at 0. So this is our secret. Now, if this is a t degree polynomial, if degree of fx is t, then only the knowledge of at least t plus 1 many points, evaluated point basically, evaluated points uh, is required to reconstruct f of x. So if you want to reconstruct this f of x, then we need at least t many points, right? So that at least t plus 1 many points, and that was the protocol. So whenever we want to reconstruct this secret s, so what we have to do, we have so t plus at least t plus 1 many parties has to come together, and they will give their shares, share their secret shares among each other, and each of them will reconstruct this polynomial. And after the reconstruction of the polynomial, they can evaluate that polynomial on 0, and they can get back this s. So that was the whole protocol. But over here, what we are given is that Alice have n minus 1 many friends, and s many friends will give incorrect information. And here we are given n as 10. In the first question, we are given n as 10, p as 8, and s is equal to 1. That is, if there are n many parties and 8 many, and the degree of the polynomial is 8, that means at least 9 party has to come. At least 9 parties have to share their values. So if 9 parties, at least 9 parties share their values, then the polynomial can be reconstructed. Now, if in this case there are 10 many parties, so these are the 10 parties, 3, 4, 5, 6, 7, 8, 9, 10. So these are the 10 parties, and this is our Alice. Okay. So Alice knows that her whatever her share is, that is correct. So Alice doesn't have Alice have not changed her share, but there is some friend over here who have changed their share. Now what Alice can do is that, so at the time of reconstruction, all of the n parties have actually all of the 10 parties basically have shared their values with Alice. Now what Alice would do is that Alice would first try these 9 points. So it will take these 9 points and it will construct a polynomial, say fx. Okay. Now in the second case, Alice would exclude this point over here. So at each iteration, Alice would exclude 1 point from the whole set, and it will try to reconstruct the polynomial. Okay. Now this will basically be constructing some other polynomial, it's a g of x. Now if this point was not changed, if it is if it was given in this if it is not changed, if it is given incorrectly, shared correctly with the Alice, then this f of x, this polynomial over here would have been equal to g of x. But since this has been corrupted, so therefore f of x would not be equal to g of x. In fact, if this was not corrupted, if this was the case that none of the points are corrupted, then Alice would exclude 1 point. So let's say Alice first exclude her own point and construct this polynomial f(x). Okay, and then Alice would exclude this point and take all these points and reconstruct the whole polynomial, and it will again get f of x, because there is only a unique polynomial that can be evaluated on these 9 points, and that polynomial is nothing but this polynomial over here. Okay. And again, if we exclude this point, this will also give us the same polynomial f of x. So if this was the case, that none of the point have been corrupted, then Alice can easily detect that by excluding one point and then reconstructing the polynomial. And each case, the same polynomial should have been reconstructed. But if one of the point is corrupted, so this will give us some polynomial f of x. So let's say f1 of x, since this is corrupted. Now, when we are excluding this point, this will again give us some other completely different point, not the same point. And again, excluding this will give us some different polynomial. So each time we will see some new polynomial, and therefore Alice can detect whether there has been someone has whether someone has corrupted the data or not. Someone has given some incorrect value or not. Okay, so therefore detection is possible with this. But remember, only detection is possible. Alice cannot identify exactly which point, exactly who has given the incorrect data. Alice cannot identify that. So this identification is not possible, but Sami secret selection scheme can be modified a little bit so that the identification is also possible. Okay, but what about the second case? The second case was that n is equals to 10, t is equals to 8, and s is equals to 1. Sorry, t is equals to 9 in the second case. And s equals to 1. So if t is equals to 9, then look at this. So we have 10 points. One is Alice, and only one is corrupted. We don't know which one, but let's say that this one is corrupted. Now, if we take only n many points, then the reconstruction is not possible. Why? Because the degree of the polynomial is 9. So if the degree of the polynomial is 9, then we need at least 10 points to reconstruct. That means all of these 10 points are now required to reconstruct. Now, if all of these points are required, so this all these evaluated points, this will give some polynomial, say if dash of x. So this will definitely give some polynomial, but whether that polynomial is correct or not, we cannot now justify, because we don't know which one of these data points have been given as corrupted data. We don't even know if the data point has, one of the data points has even been corrupted or not. Okay, so that detection is now not possible, because in the previous case we could exclude one point and construct the polynomial, and that's why each time we would get different polynomial or the same polynomial, and that will give us the detection. But now that is not possible. So that is the difference between this n is equals to t is equals to 10 and t is equals to 9. Sorry, t is equals to 8 and t is equals to 9. So this option is correct, and this option is correct. This is impossible for Alice when t is equals to 9. Okay. Okay. So now in the problem 12, we have to so we are given that p is a prime, and we have to choose the correct option. So there are 4 options that are given. So the first option says that there are p times p minus 1 over 2 monic irreducible quadratic polynomials in Zp of x. So basically we have to find the number of monic irreducible quadratic polynomials in Zp of x and monic irreducible cubic polynomials in Zp of x. So that is the task that we have to do. So what about monic, irreducible, quadratic polynomial? Now polynomials are only of two types, right? So either it can be irreducible polynomial or it can be non-irreducible. Basically, non-irreducible means that it can be reducible. And by reducible polynomial, what do we mean? We mean that it can be factored into non-constant polynomials. Okay. Now, the set of all irreducible polynomials. So, if we consider all the polynomials, so if we consider quadratic polynomials, right? So, we are considering only the quadratic polynomials. So, what is the total number of quadratic polynomials? Quadratic polynomials over ZP. So, the total number of quadratic polynomials should be p square. Why? Because the polynomials are of this form: ax square, bx plus c. So a, b, c, these are the only coefficients that we have, and we are only considering monic polynomials. So the coefficient of x square should always be 1. So we are only considering this polynomials of this form: x square plus bx plus c. Now b and c, these can be there are p many possibilities for b and p many possibilities for c, since we are considering the coefficients from zp, and therefore the total number of quadratic polynomials are basically p square. So this is the total number. Now, some polynomials are reducible, some polynomials are reducible. So we will find the number of reducible polynomials, and then we will subtract the number from p square, and we will get this number. Now, reducible quadratic polynomials. So a quadratic polynomial is reducible. What does that mean? So that means that this polynomial can be written as the factor of two factors, like this. Why? Because if this is a quadratic polynomial, let's say this x square plus x plus b, if this is our quadratic polynomial, and we say that this polynomial is reducible, that is that this polynomial do have some non-constant factors. So that means it is the only possible way that it can be written, this quadratic polynomial. That is the non-constant factor that we're talking about. It has to be a factor like this, x minus a, and definitely the other factor has to be of this form, x minus b. And why x minus b and not ax minus b multiplied by cx minus d? Why not this? Because we are considering only the monic polynomials. So both this x and x over here should have should not have any coefficient over here. The coefficient should be 1 over here in both cases. Okay, so this is the only possible way that we can write the irreducible polynomials. Okay. So now we just have to choose this a and b, but we also have to remember that x minus b, the multiplication of x minus a and x minus b is exactly equal to this. So how many ways that we can write this? How many ways that we can actually write these factors? So basically we just need to choose two elements a and b from the field zp, right? So we just have to choose two elements. So how many ways we can choose two distinct element a and b? So that is we choose 2, which is nothing but p over p. So two distinct elements can be chosen in this form. Now it also might be possible, so this is case 1, such that the two roots of this equation over here, both of these roots are distinct, so that is case 1, and the case 2 is that both of the roots are same, so this is case 2. So if this is the form of the polynomial, then how many ways that we can choose this polynomial? This is p, because we just have to choose this element a over p, so that can be chosen in p many ways. Okay, so the total number of ways that we can write this polynomial, sorry, the total number of reducible polynomial is then, sorry, it is over 2 plus p. So this is the total number of, sorry, reducible polynomial, and this should be p square over 2 minus p over 2 plus p, so that is p square over 2 plus p over 2, which is nothing but, okay, keep it at this. So this is the number of reducible polynomial. Now we know that the total number of polynomial was p square. So the total number of irreducible polynomials is now p square minus this value over here, and this turns out to be this. So this is the total number of monic irreducible polynomials. Okay, so any polynomials that we're talking about here are basically monic. Okay, so these are all monic irreducible. So the total number of monic irreducible that we have, monic irreducible. And now we have to find the total number of monic irreducible cubic. Now, if we consider a cubic polynomial, so this should be like this: ax square plus bx plus c. So this is a monic cubic polynomial, and the total number of polynomial in this case is p cube. Now, what about so how can we? So if we consider the reducible polynomial, that is, if this polynomial can be factored into non-constant polynomials, then how many ways can we do that? So there can be one way that this can be factored like this: x minus a, x minus b, and x minus c, in this way. And the second option should be like this: ax plus b and x minus c. So option 1 can be that it can be factored into 3 distinct factors like this: x minus a, x minus b, x minus c. Or it can be like this: one is a quadratic polynomial and other one is a linear polynomial, and this quadratic is irreducible. Because if it is reducible, then again it can be factored like this: x minus a multiplied by x minus b. So we are only considering that this quadratic factor must be irreducible. Okay, so first we will count this number. So how many ways can we find reducible polynomials of this form, and then we will count this number. Now if we are given this x minus b, x minus c, so there are 3 cases. Sorry, case 1 is that all roots are distinct. This a, b, c, these all roots are distinct. And how many ways can we choose this a, b, c from zp? Since zp has only p many elements, so that should be p choose 3. Case 2 is that two roots are distinct. Sorry, case 2 is that two roots, two distinct roots basically. So there are basically two distinct roots. That is either A is equal to B and C is distinct from A, or B is equal to C and distinct from B is equal to C and A is completely distinct from B or C. Okay, so there are only two distinct roots. And case 3 would be that there are no distinct roots. That is, there is only one distinct root. So all of these roots are same. So that can be the third possibility. So if this is the case that there are only two distinct roots, so those two distinct roots can be chosen in P choose 2 anyways. Okay, and after choosing that, so let's say A and B have been chosen in P choose 2 many ways, and now there can be two polynomials of this form. Either this can be one form, or the other form can be like this. So if we choose these two roots, two distinct roots, or two distinct elements from ZP, and then we can construct the polynomial in this way. So therefore, it will be twice of P choose 2. This is the total number of polynomials in case 2. Okay, and case 3 is that all the roots are same, and there is only P many possibilities because the polynomials are of this form, and the number of ways that we can construct such polynomials are basically how many ways we can choose this element A from ZP, and that is P. So the total number of polynomials of this form, x minus A, x minus B, x minus C, the total number of polynomials of this form is nothing but P choose 3 plus twice of P choose 2 plus P. So this should be P minus 1, P minus 2 over 6 twice of P minus 1, P multiplied by P minus 1. This should be P multiplied by P minus 1, and this is plus P. So this should be P cube P square minus 3P plus 2 over 6 plus P square, and this is equals to P cube minus 3P square plus 2P plus 6P square over 6. So this is P cube plus 4P square plus 2P over 6. Okay, so this is the number of irreducible polynomials of this form. Now the second one was that it has to be of this form, ax plus b multiplied by x minus c. That is, one factor is a linear factor and the other one is a irreducible. Now we know that the number of irreducible polynomials are basically this, and the number of ways that we can choose this extra element c over here is p. So this should be the total number of polynomials of this form, and this is nothing but p square minus p multiplied by p over 2. So this is p cube minus p square over 2. Now this is the total number of polynomials of this form. So the total number of reducible polynomials, that should be p cube minus p square over 2 plus p cube plus 4p square sorry this is 3p square, p cube plus 3p square plus 2p over 6. And if we add these two together, this will give us 6p cube 6p cube plus 3p cube, 3p cube plus 3p minus 3p square plus p cube plus 3p square plus 2p over 6, and that gives us I think there is a problem. Let's go over here. P cube and P cube and okay. So this value should be, so this value over here, this should be 3p cube, sorry, 4p cube, 4p cube. So p cube and p cube, that gives us 4p cube, and this should be cancelled out, and plus 2p over 6. So this is the total number of reducible polynomial. Now if we want to find the total number of irreducible polynomial, so that should be the total number of quadratic polynomial that we have already found out that to be p cube. Sorry, total number of cubic polynomial minus this 4p cube plus 2p over 6, and that will give us twice of p cube plus, sorry, p cube minus p over 6, and that is p minus 1 over 3. So this is the total number of irreducible polynomials over Z cube. Irreducible cubic polynomials over Z cube. So this should be the answer. So these are the solutions for week 12 assignments. So tomorrow we will have a summary session, and we will discuss all the problems that we have. We will basically discuss all the problems that we have, some basic problems that we have seen in this whole course. So tomorrow we will meet at 3 p.m. Thank you.